Hi, and welcome to the video on geometric sequences. A geometric sequence is a sequence or pattern in which the previous term is multiplied by a constant, and that constant is called the common ratio. That's going to produce the next term. So here is an example of a geometric sequence. Notice that to get from 1 to -3, you'd multiply by -3. To get from -3 to 9, you'd multiply by -3 again, right? And we're constantly multiplying by that same common ratio. We call it R. So in this case, R would be -3. Now, unlike exponential functions, where the base is not allowed to be negative, when you're working with geometric sequences, you are allowed to have a ratio or a base that is negative. It's going to cause those terms to alternate between positives and negatives. And we don't allow that in exponential functions because we wouldn't get a nice, smooth, continuous curve if we were to plot these. But with patterns, we don't care what that R value is. It could be positive or negative. Let's try some examples here. Can you determine what the common ratio would be of each of these sequences? 90, 60, and 40. That might not be so apparent right away. All you know is that it is a geometric sequence because you're told it is, and you have to find the number you would multiply 90 by, let's call it R, to produce 60. Well, that's an algebra question. Let's set it up as an equation. 90 times R equals 60. I can solve that. We divide both sides by 90, and 60 divided by 90 simplifies to 2/3. So that's it. That's how we find our common ratio. We do some division, right? We undo the multiplying. Notice that if we did it with the second and third term, right, 60 times that ratio produces 40, we would still get that same ratio. It would reduce to 2/3. So in this case, our common ratio is 2/3. How about the next one? This one might be even less apparent, but my suggestion is that when you're working with fractions, either you want to make a common denominator or you want to look at the numerators separate from the denominators. Now that pattern is much more apparent. Look at that, 7, 14, 28. We see a ratio of 2. And in the bottom, 1, 5, 25, we should see the ratio is 5. We just need to create a ratio that deals with the numerators as a separate pattern than the denominators. And that's easy. We can make our ratio a fraction, right? We could put a 2 in the numerator and a 5 in the denominator, and that's exactly what would happen. The numerators would get multiplied by 2, and the denominators would get multiplied by 5. Just so you know, you could still do what I did above in this example, where we could do 7 divided by the 14/5, and it would still produce this 2/5. All right, you might be asked to write the explicit formula for the sequence. Basically, that's an exponential equation with the exception that this base is allowed to be negative. So notice I'm calling it R. That's where our ratio is going to go. In front of R is a term from that sequence. I'm going to call it the nth term. And whatever term I'm putting here, I'm going to indicate what place it is in that sequence by matching up that value in here. What that's really saying is if you know the first term, this could be the first term, m over here is going to be a 1. If we know that this is the second term, this m is going to be a 2. Right? We can treat it just like point slope form, where you know a point, doesn't have to be a special point, its x value and its y value are both going to show up in that equation. Our formula starts out with saying the nth term equals. That's just a typical notation for when we're writing explicit formulas for sequences. All right, so let's do an example. I'm going to bring back the 90, 60, 40, right? We already know that that ratio is 2/3. That's kind of like finding slope, right? It's not that we're finding the constant rate of change of a line, we're finding the constant ratio that we're multiplying these terms by. So it also fits into like that point slope form model. Now, here's what you have to remember. Even though it doesn't say this, 90 is considered the first term, 60 is the second term, and 40 is the third term. There might be some reasons that we would want the first thing written down to be called the 0th term. I could think of some contextual situations, like with time, right? But when this is just a sequence of values, we're going to call that first term the first term. Okay, I can now make an explicit formula using any of these terms, including terms that I don't even see in this list if I wanted to. But I'm just going to stick to these three for now. So if I want to use the first term, I'm plugging 90 in for the a sub n. That's the term itself. And I'm plugging 1 in for its term placement, right, where it is in the sequence. See that one right there? R was 2/3. That replaced the R in the equation. The n's are still in the answer, though. That's like having your x in an equation. But we tend to use n with sequences. I could have used the second term. Then the coefficient in front would have been 60. And now my exponent says n minus 2 to adjust for that change. I could have used the third term. Here's the 40 in front. And notice my exponent is n minus 3. So we can set up an explicit formula using any of the given terms there. And just a reminder, if you've ever worked with recursive formulas before, they're typically easier to write down. In this case, the recursive formula would be saying that you multiply the previous term by 2. That is great if you want to get the fourth and the fifth term of the sequence. But an explicit formula allows me to determine any term in this sequence I want. Finding the 10th term will be just as easy as finding the 100th term. And that's the power of explicit formulas. So what do we do with these explicit formulas? We can find more terms, like I just said, right? So let's try setting this one up. We want to find the 11th term of the geometric sequence 2, 8, 32, and so on. First step that we want to do is find that common ratio. What's the multiplying pattern here? It's multiplying by 4 each time, so we know that R is 4. The next step is to write down the explicit formula. I can use any of those three terms to do that. I'm going to stick with the first term just because it's a smaller number. I want to work with smaller numbers. So notice the first term is 2. That goes right here. Because it was the first term, my exponent says n minus 1, and my R value is 4. The last step is to now find the 11th term, all right, whatever is indicated. I'm going to plug in 11 for n. So when I do that, the exponent's going to simplify to 10. This is where I can get my calculator out. I plug that in my calculator, and I get this 2,097,152, which would be the answer to this problem. So when we're asked to find a specific term of a sequence that's not the very next term, right, that's missing, we want to set up an explicit formula to do that. But sometimes we cannot find that R value so easily. So all the problems you've seen today, I've given you consecutive terms. And these are not consecutive, right? I've given you the third term in a sequence, which is 20. You're missing the fourth term, the fifth term, the sixth term, but you do have the seventh term. It's hard to see what the multiplying pattern would be because we're missing all those in-between values. No problem though. We're going to call the multiplying pattern what it is. It's the common ratio, right? It's R. So I know that 20 is going to get multiplied by R to get that fourth term. And I know that fourth term is going to get multiplied by R to get the fifth term. And the fifth term is going to get multiplied by R to get the sixth term. And the sixth term is going to get multiplied by R to get the seventh term, right? Doesn't that mean that the seventh term is really 20R to the fourth? Right? Those things have to be the same. Wasn't that also annoying to think about, like, every one of those things, like writing that down? I think we have a shortcut for that. Let's write down what we have so far, though. We know that 20R to the fourth is the same thing as 320. How could we have just gotten here quickly? Well, we know that 20 was the starting value that we had. It's not the first term, right, but it's the place to start. and we know it was going to get multiplied by a bunch of r's. How many was it going to be? I can see it here that there's 4 of them. But is there a shortcut to figure out that this was going to be a 4? Like, what if there were like 100 spaces? I wouldn't like sit there and write all this out, right? I'd want a shortcut. Can you think of that shortcut? Hopefully, you're paying attention to the number of spaces between these numbers, right? And I can count the number of spaces if I just subtract the 7 and the 3. That will always tell you how many spaces are between the 7th and the 3rd terms. So it's a nice shortcut, right? I can just count. I don't have to count that next time. I can just do that subtraction. All right, so now we're going to solve for r. I have to divide both sides by 20. Now I have an r to the 4th equals 16. I have to get rid of this 4th power. I'm going to raise it to the reciprocal power, so 1/4 exponent. A 1/4 exponent, that is something we can type into a scientific calculator. You can go ahead and do that. And it turns out we get this nice whole number of 2. This is a value you might have been able to guess, right? If you were up here being like 20 times what? I wonder if it's 2. Let me try 2, right? You could figure it out. But like I said before, what if this wasn't the 3rd and the 7th term? What if this was the 3rd and the 700th term? You're not going to sit there and guess and check this. You have to have a way that is always going to work, okay? And it might not be a nice whole number like this either. All right, so remember, we had 3 steps to find a certain term. The first step was to find the ratio. This time it took some effort, but that really is the first step. The second is to write the explicit formula. I'm using the 3rd term because I like to work with the smallest numbers possible. I didn't have the first term for this, I had the 3rd term, so I put a 20 in here and a 3 for the corresponding placement. Now I want to find the 9th term. It's time to plug in 9 for n. Simplify that, type it in a calculator, and you get 1,280 as your final answer. And that is how we work with non-consecutive terms.